Hombre,
Te voy a hacer una foto.
muy bien. Además es bien bonita. Muchas gracias, vaya. Y encima fresquita, fresquita. Mira, la pongo así que se vea.
Okay, welcome everyone. It's a great pleasure to welcome friend and colleague Pablo Pérez-González. I think you all know him. Pablo comes from the Centro of Astrobiología in Madrid, and he's an expert on galaxy evolution, but he's been very much involved in the development of JWST from the beginning, and now in the exploitation of the data, so preparations as part of GTO team of MIRI, and he's got access to many different collaborations. And she's going to update today about the work and recent results on a very high redshift universe. Pablo is also here for the winter school we are organizing this week. And tomorrow he's going to give a public lecture at the museum at 6 p.m. in Spanish. But you are also more than welcome to join. And yeah, thank you very much, Pablo, for being here. And
Yo creo que estaba un poquito cortado por abajo. No sé si influirá. ¿Vale? Okay, thank you very much, Mark, Nacho, Ginebra, for inviting me to the winter school and then organizing this seminar today. And thank you, everyone, for attending. It's always a pleasure to travel to warm Tenerife this time. It was very cold in Madrid already. Here is too warm for my taste. When I come here, I like to experience the La Laguna weather, but it's very nice being here anytime at the IAC also. So I'm going to tell you some of the work that we have been doing in the last 2 years and a half since JWST, James Webb Space Telescope, started scientific operation. This work has been done in collaboration with 4 different GTO teams that were involved in the construction of James Webb. Those are MIDIS, the team, the scientific team, one of the scientific teams behind the MIRI instrument, which is the reddest instrument, the one that goes to the reddest bands. SMILES, also working with MIRI. JADES, which is the main NIRCam plus NIRSpec GTO project. GANIFS, which is the main IFU NIRSpec GTO program. And then CEERS, which was one of the, I think there were 6 early release science observations projects that were selected like 2 or 3 years before launch to demonstrate the capabilities of JWST. And we have tried to use all those data sets to put together some papers that I'm going to tell you about. The main, let's see if this works. So I'm going to tell you about 3 different topics. I would say the main 3 results that have appeared in these 2.5 years of JWST operations. Results, very interesting results about the evolution of the universe and the early universe. And I'm going to tell you from a critic point of view, just trying to understand what we can believe and what not in these 3 topics. The first topic is, maybe you have heard, this happens all the time when we launch a space telescope to space. We see that the galaxies evolve more rapidly than what we expected. And there has been a lot of results published talking about a very efficient universe in the early times. Many galaxies are redshift larger than 10, 9, 10, like this paper by Finkelstein, where they calculated the number of galaxies redshifts larger than 9. And this is the data from JWST, and these are most of the models fall below the data, okay? This is another paper putting on the table the same results in a different way. This is a Labe paper where they found, I will talk more about this later, but they found very massive galaxies, galaxies that could break cosmology at the beginning of the mission. I will be talking much more about this. And well, this is the same, the evolution of the UV luminosity density of the universe at redshift larger than 9, in this case up to 12. And you see here the data in red. All the models fall well below the data, and I will be talking more about that. The second results that probably you have heard is that we are finding many AGN, I would say, candidates, some of them confirmed or with some indication that there could be an AGN in these galaxies at very high redshift. It seems that the universe was very active also in their supermassive black hole were very active and were probably growing rapidly at the beginning of the universe. And this is from a paper by Kochevsky. You don't see the reference because it's down here, but they calculated luminosity functions of these new AGN, many of them candidates still, and they can contribute to the global luminosity function of AGN as much or more than known quasars and typical AGN known before JWST flight. And the third result, all of them are very linked to each other, is a very efficient dust production, even in very large amounts in the very early universe. This is the highest redshift galaxy known to date, redshift 14, spectroscopically confirmed. And probably you don't see it much here, also because it's cat, but this is the results for the tau V, like the AV, and the AV is around 0.5 magnitudes, so redshift 14. For me, that's a lot. I was expecting 0 or very close to 0. And we get, with large uncertainties, not linked to the spectroscopic redshift because this is confirmed at redshift 14, but it seems for me that there are a lot of dust. And this is a galaxy that we discovered that is missed in the most sensitive instrument of JWST, NIRCam, which observes at 2, 3, 4 microns, but was not there in those data sets, in the deepest data set that NIRCam has provided, but was there at 10 microns in MIRI. And this seems to imply also a very red object, probably with a lot of dust. We don't know the redshift for this source, but it might be 14 also with a lot of dust, a lot of more dust. So those are the three different topics that I'm going to go through from different perspectives. Concerning the first one, we have been dealing with galaxies for 20 years in trying to calculate, for example, stellar masses or their star formation history from, for example, broadband spectral energy distributions. We were compiling for 20 years now, or 25, data in the optical, for example, from HST. In the near infrared, we only have like ground-based telescope. In this case, it was Keck. And then joining, for example, in the near infrared con Spitzer, fitting stellar population models and getting stellar mass and star formation histories in general. Also, we were calculating the amount of dust and the amount of obscure star formation with data, broadband data in the far infrared. For example, this is, well, seminal work in the local universe by Calzetti with IRAS data, I guess, at that time. And then we had other telescopes. In fact, we have been doing this. This is going very slow. I'm going to try to move here. So this is probably one of, or the first impressive image from that Helmut knows very well in the far infrared submillimeter wavelengths where we observe a very dusty galaxy at high redshift. Okay. From Hughes et al. The reference is down there, but you don't see it. This is the evolution of this type of observations done in the 2003 to 2010 period with images of one specific region in the sky, the extended growth strip with the Spitzer 24 micron and with Herschel 160 microns. You see that we evolve a lot from the submillimeter scuba times, and we see individual sources, one of them quite faint, 160, but there and very well isolated at 24 microns, but still with not much morphological information. I'm going to do a zoom here there, and this is the same 24 micron image, zoom in a lot, okay? So you see the individual pixels and like a green circle around. It was the green circle that you saw in the previous image. And I'm going to tell you how this looks for NIRCam, for JWST. So that source looks like this for NIRCam, okay? And you with NIRCam is impressive for, in my opinion. We don't reach 24 micron. Well, we reach 24 micron, but we don't reach 100, 160 or so millimeter. But at this wavelength, we already see that this galaxy has a structure, and in fact, it has some part of the galaxy is where the dust is concentrated. We see with morphological information where dust is located in this galaxy. So we can do a much better job in determining the dust content and the dust effects on the determination of the properties of this galaxy. So now you can do the same job that I was showing you before with a paper by Popovich in 2003 doing SED fitting. Okay, so I hope you agree that this looks very similar to the SED that I was showing before. Okay, but that galaxy was a redshift 2, the entire galaxy. Here you see that in that galaxy they were using micro Janskis. Here I'm using nano Janskis. Okay, and in fact I could even use pico Janskis. I want to be the first one here to show an SED in pico Janskis. So we have an SED at 100 pico Janskis. If you are old enough as I am, you are not used to these units, and maybe you understand better magnitudes. We are talking at magnitude 33 source, okay? If you are in the JWST business, you will know that we don't detect galaxies at magnitude 23. We detect galaxies up to magnitude 31 because this is not a galaxy. In fact, this is 1 pixel of an extended galaxy at redshift 3.7. And the point here is that with JWST, we can do the same job that we did for 20 years, but not for an entire galaxy and not for redshift 0 or redshift 2. We can do it for redshift, I think it's almost 4, and for pixels. There are like 1,000 pixels. All of them are not independent. I'm doing this in a pixel by pixel basis. They are correlated in 9 by 9 or something like that, or 3 by 3, sorry, like 9 pixels. The 9 contiguous pixels are correlated. But then the idea is that if you do the SED fitting in a pixel by pixel basis, you're considering parts of a galaxy. And parts of a complex system are more simple than the whole system. So you can get much more robust results. And if the dust is concentrated in one part of the galaxy and not the other, there you will see the dust and you will not have the whole degeneracy between age and dust that you have when you integrate the galaxy as a whole, okay? So you can do SED fitting. This is going very slow, but it's going quick in my screen. So it's not broadcasting very well, but I'm doing pixel by pixel basis, and it's showing up there. And then I'm showing the integrated star formation history as you run your code through the galaxy, and you sum up everything, and you get the star formation history of the whole galaxy, but with a pixel by pixel basis analysis, which should be more robust, okay? This is going very slow. If you can see it, it's going very quick in my... Okay. So this is what we did for this galaxy and others. And in fact, you can do funny things like before, one of the things that you have to do first with this kind of data is getting photometric redshift for everything, spectroscopic redshift, so if you can. Now we can do a photometric redshift, but not with the whole galaxy, for pixels of galaxy. Of course, you won't believe the redshift of every single pixel, but you have independent estimations of the photo Z for one galaxy in different parts of the galaxy that have different SEDs. So you can join all the information together. And for example, in this galaxy, we show that this part over here that was a very bright near-infrared source that was discovered by HST is a different galaxy from this part over here that appeared when JWST data arrived. In fact, it's 2 galaxies. There is an overlap there, one at redshift 4 and another one at redshift 2. So you can do photos in 2 dimensions. Here we were interested at redshift 4 and above, and we removed the upper part. So you can do much better than what we were doing before. And you can do maps of interesting parameters like stellar mass or attenuation. If you want, I'm going to go to the sample that I had before. If you do the SED analysis, you recover large AV numbers exactly in that red region that I was showing you before. That explains the 24 micron and the Herschel emission in this galaxy. So with that, we did an analysis in 2D for a sample of near-infrared faint, mid-infrared bright galaxies. This is more or less, this is what we called before JWST flight HST dark galaxies that were discovered because they were very faint or undetected in HST, but they were bright in IRAC. Now these are the typical galaxies that JWST detects, and more or less it gives you a stellar mass selected sample, complete sample at redshift larger than 4. Okay, and we did this 2D analysis in this sample, and we found that this kind of the galaxies that JWST is typically detecting in the mid-infrared comes in 3 flavors. There are three different types, a triality we call it, okay? And the main results are in these 2 plots. It's a huge mess. I agree with you probably that you were thinking about this, so I'm going to break these plots for you. So the first type of galaxies that we found in these JWST surveys was quiescent galaxies. Quiescent galaxies are redshifts typical of 3-4. Before we knew that there were a lot of massive galaxies, massive quiescent galaxies at redshift of 2-ish. Now we are extending that to redshift 3 or 4 in this paper, and now there are redshift 5, 6, even 7, 8. They are also talking about quiescent galaxies, although the type of quiescence is a bit different. These galaxies had a typical star formation history as what you see here. They are extended in many of them are extended. Maybe not the very high redshift, but you have several resolution elements, and you can do the 2D analysis. These galaxies live quietly for maybe a giga-year at the beginning of the universe, starting very early. I will come back to that later. Maybe at 10 solar masses per year, and they had a huge burst that increased the star formation rate, the average star formation rate in 200 mega-year-old time chunks by a factor of 3, 4, and then they decayed, and now we are seeing them like several mega-years, several million years after the big star formation event, and they are quiescent right now. Okay, so I'm going to stop about those triality and tell you more about quiescent galaxies with another paper that we put together. What I showed you was SED fitting to get stellar population properties with broadband. Some of you will say, well, with broadband, you cannot do anything. But I will tell you, well, I'm doing this in 2D, so you can do something. But I will agree with you, and we can do better if we have the spectroscopy. JWST gives you amazing spectroscopy. I'm going to show you one example. This is a famous galaxy. It was a quiescent galaxy at redshift 3.7 discovered by Glazebrook 2017. In that same year and the year after, some other authors, Simpson and Schreiber, said that, well, this galaxy is not as quiescent as you say, although you have spectroscopy. There is ALMA and SCUBA emission from this galaxy. But the ALMA was discovered that was coming from, not from that galaxy, that quiescent galaxy, but from a galaxy nearby. And they called these galaxies Hyde because there was a hidden galaxy, and the other one was Jekyll. So this is Jekyll and Hyde. Jekyll is the quiescent galaxy, Hyde is the dusty galaxy, both at the same redshift, 3.7, okay? Both are companions. This is pre-JWST. So this is how JWST sees these galaxies. This is an RGB image constructed with IFU spectroscopy. In green, you see H-alpha. And then in red and blue, it's broadband constructed with low resolution spectroscopy that covers from 0.6 to 5 micron observed, okay? I will show you this. And this is a huge mess. You have here Jekyll, quiescent, I will show you an SED, Hyde, but then we saw things around, and in fact, things that are very, very bright in emission lines. In fact, my interpretation of this source now is that we are seeing nebulous systems, gas-rich systems, maybe with no stars around, probably gas that has interacted in somehow with the two galaxies, two massive galaxies in the center. Okay. That was constructed with low resolution spectroscopy, but we also have high resolution spectroscopy, 2700 resolution, 2700, and you can do kinematics, and the kinematics is amazing. So this is Jekyll, Hyde. We call this West, Mr. West, and this is Eastfield, based on other two characters from the book, Enfield and Mr. Guest, okay? These are the gaseous systems, and you see here that in this gaseous system, you have velocities from minus 850 kilometers per second with respect to Jekyll to minus 100, and here you have up to 150 kilometers per second with respect to Jekyll. So there is huge, this is the velocity map in Oxygen 3 compared to what we saw before also with C+ in ALMA data, okay? There is a huge, so that gas seems to be rotating. I will show you a map in a minute. You can do BPT diagrams, and these regions fall up here in the AGN region, also in the shock region. And my interpretation is that there is a lot of shocks right here. But maybe they are photoionized by the AGN. I will come back to that in a second. And we also see another system that you were not seeing in these RGB images. There is absorption just in front of Jekyll. There is absorption in sodium, a huge sodium absorption, which is redshifted or blue shifted, I don't remember, with respect to Jekyll. It's not at the same redshift, it's slightly, well, it's gas coming towards us in front of Jekyll. Okay, this is Mr. Sodium, also based on another character of the book. So our interpretation of the system is this one. You have the observer here, we are saying Jekyll here, we think that Hyde is in front of Jekyll, and probably it has an obscure AGN or a dead AGN, and we think that this AGN photoionized and shocked material, gas material over here, and we are seeing tidal tails around this whole system. So we are seeing probably feedback in motion, but feedback also linked not only to Jekyll, which is completely dead, no signs of AGN of any type, but maybe also with the companion that is coming, which is very massive too, is coming towards Jekyll, okay? This was based on stellar population modeling. We had the collaboration of Nacho Martin Navarro, who probably is working with the Winter School people. He did an amazing SED fitting for R2700 spectra. Each one of these spectra is an annulus here. It's not a whole galaxy. It's an annulus. You can do this job with a spatial resolution, and you can calculate metallicities and abundances with high accuracy. This is for Jekyll, solar metallicity. The metallicity goes down a bit towards the outskirts, and is very alpha enhanced. And you can do the star formation history. This is the star formation history. I want you to remember the star formation history that we calculated for the general population with broadband. This star formation history and this one are very similar. A huge peak, staying for 1 gig a year, then a huge peak. Here we have more better temporal resolution, so you go up by a higher amount, and then it decays, and we are seeing like 600 million years after the big event, the star formation event. The second type of the triality of JWST sources is dust obscure galaxies. Dust obscure galaxies, some of them, sorry, this is going very slow. Okay, some of them in our sample were confirmed to have MIPS and Herschel, and SCUBA, sorry, and Herschel detections, but most of them, like 60% of them, did not. JWST is going deeper than infrared surveys. So we detect many more dusty galaxies at a lower dust content, okay? We are more complete in that sense. For these sources, I'm not going to say much. Well, we did an analysis of how well we would recover the dust content, and we get rid with this 2D analysis of the dust age degeneracy. We don't get much lower star formation rates for these dusty galaxies because we are doing in 2D, and we can isolate where the dust is located and have a better understanding of the whole star formation rate of the galaxy. But I'm going to concentrate in one type of galaxies that are also dusty, and in fact in this main sequence plot are up here in green over here, which is what we call in that paper, well, these are the quiescent galaxies, but what we call in that paper extreme emission line galaxies. There was a type of sources, these sources that we were investigating. I told you that it was faint in the near infrared, bright in the mid infrared. So we're selecting them with a color. And it was a color 1.5 microns minus 4.4 microns, okay? You can be red because you are quiescent, because you are dusty. In this case, we understood that they were red because an emission line with a huge equivalent width was going into the 4.4 micron band, okay? Oxygen 3 at redshift 6 to 7 goes exactly in that region. So extreme emission line galaxies at redshift 6, 7. If you look at the morphology of these galaxies, you see that they are compact and red because they were selected as red, okay? And you probably have heard about little red dots. These were the little red dots. And I'm going to tell you now more about little red dots, which is a quite hot topic in JWST studies. Little red dots first came in a paper by Labé, put together in 2-3 weeks after the first data was released. And he was looking for double break sources, okay? Sources with a Lyman break and a Balmer break at the same time, looking for massive galaxies, and he found some galaxies where that were not exactly double break sources. They had a Lyman break, but they were very blue in the short wavelength channels up to 2 microns of JWST, and very red quartz of that point up to 4.4. They had like a V shape we call SED, okay? Blue and red in different parts of the SED. Blue short wavelength, red long wavelength, and they calculated stellar masses, and they came to stellar masses well above 10 to the 10, some of them about 10 to 11, redshift 7, 8, 9. These galaxies were called to break cosmology, too massive for their redshift. They could have many more baryons than the density of the universe. Okay, you probably, if you were listening to this news, you heard about them. And they were exactly as the extreme emission line galaxies that I was telling you before. Very point-like in the red, little red dots. Okay, they didn't call it little red dots at that time. We found these kind of galaxies also in samples detected with a color. In this case, I told you it was 356. In fact, not 444, as I tell you before. I already told you about this type of a subsample of the selection that we were doing with a red color. Okay, and they were up there in the main sequence, and they were little and red. But when the little red dot name came into being, okay, it was in a paper by Mathie. They were looking for galaxies with broad emission lines in GRISM data taken with NIRCam. NIRCam can take GRISM data at resolution 1400, okay, and you can see there a spectrum for every single source in your field of view, okay. The brightest will have some emission lines, and they were looking for emission lines that were broad, okay? With that resolution, you can detect broad lines. And they detected like 10 of these sources which had broad components in H alpha, broad components meaning above 1,000 kilometers per second, and typically 2,000, 3,000, okay? And they were looking for these galaxies, but then they look at the morphology. And the morphology was little and red. So these were little red dots, and they identified these little red dots based on the broad line components with AGN. Okay, and now is where everybody thinks that a little red dot is in an AGN, and an AGN is a little red dot, and I'm going to go into that in detail. Okay, so we went ahead and studied a sample of little red dots, not selected spectroscopically like Mathie, but more photometrically like Labé. Okay. And this is a compilation of the RGB images of these galaxies in good south. Okay, so the possibilities of the nature of these sources have been put. Several of them have been put on the table. I have mentioned some of them. They could be, I didn't mention, but some of them could be galactic objects, brown dwarfs. In fact, like 20% of the photometrically selected little red dots are confirmed to be brown dwarfs, even with proper motions calculated with JWST. Okay, and also with the spectroscopy, and they have beautiful absorptions of water and CO2 and whatnot. I'm not in that topic, but it's amazing the spectroscopy. They could be two massive galaxies at redshift 7, 9. I remember Labé's interpretation, first interpretation. They could be, dusty galaxies at redshift larger than 4. Okay, similar to the galaxies that I was telling you before. They could be type broad or narrow line region AGN, like type 1 to 1.5, as the Mathie interpretation of their selection, which is different. Okay, they could be multi-personality AGN. I will come back to that in a minute. Okay, I have not told you about that, but I will come back to that in a minute. And well, I'm putting on the table this question, so my answer is relevant just because I'm putting the question on my table. I also invite you to go to that web, tinyurl.com/sexto-LRDS. That's a poll that I put together at the beginning of the year, and I'm trying to see how the community might change or not their view on this little red dot thing, okay? And my answer to the nature of these sources, I have already told you that some of them are galactic objects, but between the other interpretation, my answer is that you should ask MIRI, because everything done until this work for this type of sources was based on NIRCam and NIRSpec, okay? And MIRI was not saying anything. And we in this paper, we try to say something about with MIRI. Why? This is the other interpretation that currently is the most famous one, or the accepted one for many of the community, based on a paper by Labe in 2023b. So a second paper where he changed his mind, although he didn't say it, but he changed his mind from very massive galaxies to this. So this is the SED, V-shape, blue in the short wavelength, red in the long wavelength. They also had ALMA, and they saw that the ALMA was quite low, and the ALMA was constraining the solutions for the SED fitting a lot. You couldn't fit easily with stars. So what they claim is that, in fact, what you were seeing is the UV was dominated by an accretion disk from an AGN, but the accretion disk, which you see in type 1 AGN, was accompanied with also a dust torus. And you were seeing the dust torus and the accretion disk at the same time because of some funny geometry or because of scattering, okay? And you were seeing at the same time the accretion disk in the UV and also the torus in the infrared. And it explained the SED very nicely. Also, the very faint detections in ALMA or upper limits, which is what you can believe for most of them. Okay, so this is what I call a multi-personality AGN or a schizophrenic AGN, because you have like type 1 and type 2 at the same time, seen very bright in both wavelengths. Okay, but you can see that the stellar population models and the dust torus models differ a lot in this region, and that's exactly the region covered by another JWST instrument called MIRI. Sorry. Thank you, Christina, for the water and for the cup. I'm taking it to Madrid. So we selected little red dots photometrically. This is the standard way. We come with 31 of them after removing brown dwarfs. These stars are the brown dwarfs that we selected and we removed. Okay, 20% of the sample. And the key here is that we had very deep MIRI photometry in multiple bands for these sources, and we have a spectroscopic redshifts for 55% of the sample. So this is very weird. Also, 5 years ago, we couldn't think about having a 55% completeness in a spectroscopy in high redshift sources. Okay, so this is amazing. The typical redshift of this source is redshift 7, and you don't have much answer to this due to photo-Z, because the photo-Z's behave very well for this, with this photometry. And we went to SMILES, the SMILES survey, which is a MIRI survey in all bands. The quality of the SMILES data is exemplified in this plot. This is what we saw at 24 microns for these 5 sources at redshift 1 to redshift 3. There is like a Stefan quintet at high redshift, and now we see much more morphological information where we only saw a blob before. So we had this SED from Labe, which I have distorted because I'm going to translate to the average SED of our little red dots. These are all the NIRCam data points for our 31 little red dots. And you can see, and here is the schizophrenic AGN template in red of Labe. And you see the blue short wavelength, red long wavelength. This is a QSO spectrum, average spectrum. Okay, and it doesn't fit this region very well because they say that you need a dust torus, and this is an obscure AGN quasar spectrum. Okay, and this is the MIRI data. The MIRI data doesn't go up here. You are not seeing the torus as what Labe was saying. Okay, there is not a bright torus in these galaxies. The MIRI data is ruling that out. In fact, you can say, okay, but maybe the dust torus is not as bright. You got to scale it down. So if you scale it down, for example, and you say, well, this is the average little red dot SED. If you scale the torus down and you say that it dominates at 2 micron, then something else has to explain the emission at 1-2 micron rest frame. Something else, 1-2 micron rest frame, is where stars dominate the emission in typical galaxies. So maybe their stars are dominating. Okay, and this is what we did. SED fitting with several components, including stars, an AGN of different types, dust torus, accretion disk, and strange combinations of them. In fact, you don't have to go to AGN at all to reproduce this type of SED. This is a template extracted from a compilation of C.V. Morgan in 2007, where they were trying to see how very compact starbursts look like, very compact dusty starbursts look like. Very compact meaning less than 300 parsecs, okay, with a lot of OB stars, very, very young, and a lot of dust. And then some of those OB stars will be in clear areas, or there will be a lot of scattering, and then they reproduce the UV part, more or less, at least until here. And then the red part is dominated also by star, by the extincted part, and the very bright infrared part at 2.5 micron will be dominated by very warm dust heated by the young stars, not heated by a supermassive black hole, as the aging interpretation tells you. So we did some detailed modeling, not only with a stack, which is what I have shown you, but also with individual galaxies. Here we have several recipes, several people running their models with different tweaks, okay? But there are two things that I want to stress here. One is that we consider that these SEDs of little red dots should be composite. You should have two different types of things. Very extincted starburst and a blue starburst, or a very scattered starburst, an AGN and a starburst, maybe dominating the UV1, the infrared, but you have to combine all those ingredients, and we combine them in 4 different ways with different codes, synthesizer AGN, prospector, okay? I'm not going to go into that detail. And the other interesting thing that I want to mention about this modeling is that you really have to account that these galaxies are so compact, and they are relatively bright in MIRI, but not as bright as what the dust torus was predicting, dust torus models were predicting. But you really need to have a lot of warm dust. So you really have to be careful in what dust models you use. These are typical dust models of local galaxies that typically the dust typically at a temperature of 20 Kelvin, they peak at around 100 micron rest frame. The SEDs of these objects probably peak at 40, 50 micron rest frame. That means that they have like 100, 200 micron, 200 Kelvin dust. And this is the models that you see right here that they peak much less. So we did this exercise, quanting with MIRI data for the 31 sources. Some of them were detected in many bands, MIRI bands. We call them the golden sample. And we could reproduce the infrared part with this red model, which is dust heated by star formation. In this case, we needed an AGN here that we could be seeing in the blue, but not dominated the mid-infrared, okay, and the near-infrared rest frame. This is one of the modeling recipes. These are the others, and we obtain similar results. This is another galaxy. Again, in red, we show the dust heated by a star formation. And here you have some contribution from dust heated by a supermassive black hole, but not that large. Same for the other recipes. This is another type of source. The slope was so prominent, so high so large in the mid-infrared that you really need a torus model. And in this case, we had to have this orange, which is a extincted QSO model, okay, a dust torus. So we did this for all galaxies, and at the end, we came up with an analysis of what is the incidence of AGN in these little red dots, selected photometrically. So we did this in different ways. The first method, we saw that we had 55% of our samples, 18 galaxies of the 31, have a spectroscopic redshift and spectroscopy. And for those, only 3 have broad emission lines. So 3 out of 18, it comes to 70%. Only 17% of the little red dots with the spectroscopy are confirmed AGN because they have a broad line emission, okay? Confirmed with quotes. I will go back to that in 30 seconds. The second method is based on number densities. In photometric selections of little red dots, we come to a number density of 10 to the minus 4 galaxies, little red dots per cubic megaparsecs. When you go to Mathie paper, they obtain very less, okay? They obtain typically 10 to the minus 5. So just the number density comparison comes to a 20% incidence of AGN. Incidence of AGN, meaning AGN that dominate the SED in some parts of the spectrum, okay? We did the same with the SED modeling that I told you, and we saw if the AGN dominated the UV, the optical, and the near-infrared in rest frame, or several parts. And we come, this is more uncertain, but 20 to 50% depending on the redshift, on the spectral range. This is in our paper. I want to put on the table some other information in the literature. People have try to detect to see if these galaxies, these little red dots, were detecting X-ray. There is 1 out of 1,000 that is detecting X-ray. People have done stacking and they see nothing. So there is no X-ray data. Maybe this is very high redshift. Maybe we need Athena or something like Athena to recover X-ray emission, but there is not a clear sign of an AGN there based on stacks of X-ray data. The second extra information, which is not linked to my papers at all, I think it's clear that there needs to be a lot of dust, very warm dust, and the dust can be heated by OB stars or by a supermassive black hole. So that there we have an uncertainty that we still need to clear. And the third thing is that people are even trying to understand if the broad emission lines could be linked to something else. Some people are claiming that these are so compact and there are so many galaxies in such a small volume, the densities are so large that even kinematics of the stars can explain that emission. This is a paper by Bagen. And there is also some people that claiming that there could be huge amounts of outflowing low Z gas, low Z, because you see broad emission in H alpha or in H beta, but not in oxygen 3, for example. And then that could explain the broad components. So the broad components would not be linked to an AGN. People are exploring those possibilities too. Well, in my paper, we calculated then stellar masses. The typical stellar mass that we get is 10 to the 9.5, nothing like 10 to 11. So I think that is past us, that interpretation. Even Labé reinterpreted the same sample in their second paper. So I think that's maybe there is 1 out of 12 or 13 sources that could be very massive, but not the numbers that they were putting on the table. And we also calculate the typical attenuation. The typical attenuation, bolometric attenuation, is like 3 magnitudes. That means that 1 of every 10 photons survive and arrive to us. There is huge extinction here, okay? And this is the typical star formation history. The star formation history, well, I'm going to go through this. Hopefully I could, because this is a summary of the little red dots thing, but I think I have spent here. But I wanted to arrive to this, a link between little red dots and quiescent galaxies. I didn't mention, but in the star formation history of the little red dots, typically we were getting ages below 10 mega years and star formation rates of several hundred solar masses per year. Exactly the peak of the quiescent galaxies at redshift 3, 4 that we were obtaining, or Jekyll galaxy. So I think these two populations are linked. Maybe we are seeing the peak of the star formation in quiescent galaxies. These galaxies, little red dots, are typical redshift 7, and then they die, and we are seeing then at redshift 4, 3, and then later at redshift 2 when they accrete more material. I think I want to go to a couple of more things, quick things. We are trying to understand if there are little red dots even beyond redshift of 7 or 9, which is the limit of NIRCam. And this is one of the sources that I told you at the beginning. This is one, the deepest observation taken with NIRCam at 4.4 micron, which is the reddest NIRCam band. This is 5.6 micron, which is also already a MIRI band. And there is nothing in these two, in this region, which is the same. And then we went to 10 micron. We exposed for 10 hours and we saw a source. This is a very red source, a NIRCam dark source that we call it, missed by NIRCam and recovered by MIRI. If you do the SED fitting, if you start with the average little red dot SED fitting, and I do the same job as I did before, and I pass to the SED fitting built with stacking NIRCam data like crazy, okay, and trying to recover some flux at 4 sigma or almost 5 sigma level, the typical SED of this source that we call Cerberus is very red, is very similar to a little red dot, but a little red dot at redshift 14. Okay, so this could be a little red dot at redshift 14 missed by NIRCam, and MIRI is detecting this kind of thing. We have demonstrated that we can do that with MIRI, going more into the mid-infrared at 10 microns instead of cutting at 4.4. And the very last thing I want to talk about is I'm going to go back to this plot, very messy plot that I told you and I have broken, okay? These are all the galaxies that we have in the initial paper, and these are the star formation histories in this specific star formation rate versus age of the universe plot. This is all the tracks of these galaxies. And here I plotted the galaxies that we knew that were at high redshift at the beginning of the JWST mission. Now there are many more, but more or less they are all over here. But what we saw is that all these galaxies, the star formation history that we believe much more because they are made in 2D, okay, remember, they imply that the bulk of this of the star formation in these galaxies occur in this region over here. So we were only probing directly at redshift above 10, the very peak of the star formation. Okay, we should have many more galaxies here. In fact, you can see this in another way, is that the galaxies started their formation very early. There is a very efficient universe in early epochs, redshift 30, 40, or 2030. Okay, so there is another paper that I wanted to talk about to finish, is that we went also there with data from the GTO team, from the MIRI GTO team. We had a very deep observation of 5.6 and 10 microns, and that's how we discovered Cerberus. But in parallel, with JWST, you can observe with two instruments in parallel. We have also extremely deep NIRCam data, and we could try to identify very high redshift sources. Very high redshift sources, these are our sources in this very deep survey. These are the other sources that were discovered by other surveys, and we could go much deeper than them because our data was much deeper at that time. Now it's one of the deepest, but not the deepest. At that time it was the deepest, okay? And we built luminosity functions, and I'm going to go past that, and we constructed the Madao plot, okay? This is the UV luminosity density, and this is our data compared to others, okay? And here we compare with some models. For example, this is the illustrious models. But in this comparison, in this paper, we also try to be careful. This is the evolution of the UV luminosity density of the universe above redshift of 8 if you consider the whole size of the halos in illustrious, okay? But our galaxies, we measure the photometry and the star formation rates and the UV emission in small sizes, in 2 kiloparsec size apertures, okay? So if you go back to illustrious and you just take the center of the halos, in 2 kiloparsecs, you arrive to this. So we are like 10 times or more above, the observations are 10 times or more above what the illustrious says that the universe should be emitting in UV. I'm not saying from stars, it could be from AGN, but in terms of photons, there is many more photons at high redshift than what illustrious is predicting. This is the same for other two models, Eagle and Flares. And here we discuss that when you do the UV luminosity function in illustrious or in Flares or in Eagle, you integrate the whole luminosity function. But the typical stellar mass of those galaxies is 10 to the 6 solar masses. The masses that we are obtaining, the stellar masses that we are obtaining for these high redshift galaxies, that could be biased, but typically they are 10 to the 8, 10 to the 9. So they are much more massive. So if you want to compare apples and apples, you should cut your models to the same stellar mass. And then if you compare the UV luminosity density for stellar masses about 10 to the 8, galaxies with that mass or higher, you are far away from the data. So the models really have a problem here. This is another types of simulations. They were exploring cold dark matter versus warm dark matter being this line, so it fits better the data. Okay, and this is all the models. So this is my summary slide. The title of the talk was the good, the bad, and the ugly. The good in JWST results. I think there is an agreement that the universe was very effective forming stars and producing UV photons. And we have arrived to this from several perspectives. Directly probing redshift larger than 8, I have just shown you, but also from the fossil record of star formation histories of galaxies at redshift 3, 4, 5, okay, of different types. Both methods agree very well. And the star formation histories are quite robust to the analysis, okay? That's the good. The bad, I think that we have huge selection effects. People identify little red dots with AEN, but when you talk about little red dots, there are different types of little red dots. You have the little red dots that a guy, Jordan Mathy, very well, a very nice paper, he put on the title. They were selected spectroscopically, okay? When you go to photometry, you select little red dots, but they are different. In fact, Mathy and our paper observed the same or used the same area. He had one little red dot with a broad component. We had 31. Okay. Then other people detected broad components in other galaxies which were fainter and not accessible by the data that Mathy had, but only 3 of 18. Okay. So we have to be very careful. Also, that interpretation of the very massive galaxies are very high redshift. I think we have to go through past that. I told you, even Labe put together a paper saying the contrary of what he said before, in reinterpreting the data. Both papers were very, very nice, but I think we are learning in both of them and with the other papers that we are putting together. But I think we have to be careful with the interpretation. And the ugly, I think the ugliest part of what we have right now with JWST, and the ugly, I like the ugly part because ugly guys can get prettier somehow, because they have a nice character or because they are very nice persons, okay? So the ugly part can get good, can get better, okay? The ugly part for me of JWST results is that the data is so amazing that we don't have the tools to analyze it. There's so much information there that is really, really very, very difficult to interpret the data that we have. For Jekyll and Hyde, you saw the sketch that I had there. The data was amazing. And we had low resolution spectroscopy, high resolution spectroscopy, kinematics, everything. But interpreting everything at the same time is very, very difficult. I think we have to get prettier in our techniques. If you want to get prettier and talk more about this is my last slide. We're organizing a conference in Toledo next year, May 2025, where we'll be talking about this and many other JWST results. You are all welcome to come there. I will be happy to see you in the conference. Thank you very much.
Thank you, Pablo, for this really interesting talk. So it's time for questions.
Hi, Pablo. Very nice talk. Well, I have a lot of comments, but let's start with the little red dots, of course. No, something that I failed to understand is like if these objects do not challenge our understanding of the universe anymore because they are not so massive anymore. No, they are not so star forming, I guess. So why are you so keen in killing the AGN? I mean, is it that important to demonstrate that they are not all AGN? I mean, I understand the point of doing like an object-by-object analysis to understand what's going on and to learn how to reproduce the SCDs. But is it so relevant, no, to assess? Also because there is so much uncertainty in the AGN property at high redshift, no? Because you mentioned broad line AGN, but broad line AGN are only some type of AGN, no? There are also narrow line AGN, and there are AGN that are not detected in the X-rays, as you have mentioned. So the properties might be completely different, no? So, yeah, I don't know.
Those are like 20% of the population of the general population of galaxies. If we believe stellar masses of around 39.5, I think more or less people are agreeing with that, or even more. Okay. The key here is also that the little red dot discussion is linked to other discussions. For example, the large amount of UV photons that we see in the UV density. You can understand that plot in terms of formation. Okay, there's much information, but maybe it's not that. Maybe it's that we have too many UV photons because there are too many supermassive black holes. And maybe for that you need supermassive black hole seeds. If you have supermassive black hole seeds or direct collapse, you are throwing farther away in the universe, which we are not probably directly, like maybe with a quantum record. So it should help to understand these very phases of galaxy evolution that we don't understand. The simulations have a lot of time there. If the universe is more efficient, I would say not forming stars, but forming UV photons. And those UV photons could be from stars, or from AGN, or from holes in the material. We also see a huge, so we also see that it's not my thing, I haven't said anything to talk, but people have to keep it in mind that typically what we're expecting to see very low metallicity high and aggressive. We have reached a limit floor around 5% lower. We don't see anything, even a super big things like that. So again, it seems there seems to be a enhanced production of photons. Everything is linked. So the role of supermassive black holes, which you brought to AGN, I think it's very important. So understanding if this is a phase where supermassive black holes are growing rapidly, or they have huge amounts of star formation, but accompanied with a lot of dust production. I think it's very important.
You don't need to convince me about this.
How at the end and quickly that goes into a feedback mechanism that stops stuff. So everything is linked. So although I think there is a lot of fuss about this little red dot things, and it's a limited galaxy population. I think the questions that is putting on the table are important. And this population is interesting to address, which are very high. And for that, we really have to understand which is the source of the emission and different ways of putting this and what
Yeah. I understand that and I agree, but I just feel that you are more keen in killing the AGN from the red dots than in favoring them, no? And based on what we know in the local universe, okay.
And then the interpretation of that, I don't think is robust. So it's very important that we understand how we interpret the data and also what the community that is studying AGN in the local in detail or creating galaxies in detail understand that what are the we are telling the community maybe it's not accurate.
We were all brought up on the standard lambda CDM. How much of the lambda CDM is now in question as a result of these results? But small galaxies form before large ones in that case. High metallicity galaxies form before low metallicity galaxies.
There are some models that I think are Astrobiologist others that don't touch standard galaxy at all, but work on feedback mechanisms. I think feedback mechanisms, the variant physics, that's why this is already, I think it's more important, or we can address many more questions on variant physics and feedback mechanisms, feedback-free preparation, that is why they are claiming that there could be we will be seeing a hybrid or some kind of
positive rather than negative feedback.
Feedback free, which is zero feedback or even positive.
Positive feedback from AGNs.
The cards and if negative feedback might start to dominate from AGN. I'm not a very big fan of AGN feedback. That explains my and then galaxy time. But at the beginning, my interpretation of this, of course, is that we are not growing in our galaxy. I think we should understand better and we should take more on feedback mechanism, reduction of feedback, or positive feedback. I think very good. That might be linked to some kind of work that matter that is important in very early books, and the numbers, the CDM, the whole that matter gets more important to
Thanks.
Hi, Pablo. Very nice talk. I have two questions. The first one is like when we talk about little red dots, we seem to confine them to redshift 6, 7, and above. So I would like to ask you what are the possibilities and limitations of exploring this population at a lower redshift that maybe is easier also to trace other range of properties? That would be the first. Okay. Yeah.
They are trying to tweak a bit the cosmetic direction to try to go for lower redshifts. And we are not being able to detect this kind of source with overseas of very few overseas breed. It seems that it's a population that was very important, at least progressive 9, progressive 4, and then indicate. Progressive 9 above, we don't know, maybe Cerberus.
Yeah.
There are little results of high redshift, but Cerberus are people that is so. People are to tend to define some of that galaxy with a lot of the age. But we are trying to detect little results and lower redshift. Even some of the sources that people have observed spectroscopically, there are papers about specific sources with the spectrum of these sources. The branch one that they are free, you can find that they are bright. They think that they are little light, but they are not exact. They are not, the blue one is not there. They are extended, not exactly what we are seeing. But it seems that it's a population that is very relevant around what you observe, and it indicates very hard. The core of massive creating galaxies.
Okay. Okay. And the second question was like, okay, let's assume that portion of these little dots actually have AGN activity. So I wonder if there has been any study comparing at this high redshift these little red dots with other galaxies that are also identified as AGNs, but do not present in this particular fashion of being a very red compact object. And if the properties are somehow different or very similar when we reduce the scope to the very center of the galaxy.
So, results are blue all the way. If you have some of them, you start to see the torus, but then they get redder. So this is like something in between. So they are okay. Morphologically, many of the area that we have detected with X-ray and all that, I think you high redshift now, particularly for it low. Yeah. They are standing sources and then beautiful spirals. These are quite different. These are high redshift. The quasars are similar to this, but the quasars don't have the high redshift quasars. I showed you the average spectrum of quasars. They are blue all the way. They don't have a red band. When you calculate supermassive black hole masses, these galaxies seem to have masses similar to quasars. And the stellar masses are difficult to get. People sometimes just pick the UV, and in the UV we are seeing that that is dominated by stellar mass by stars, and then the stellar masses are around 10 to the 7.5, 10 to the 8 solar masses, and then these objects would have supermassive black holes. That's something that we have been discussing in the JWST literature also. But if you think that the infrared can be also dominated by stars, then the stellar masses go to 10 to the 9.5, then they are not so supermassive black holes, but they have similar supermassive black holes to quasars. Okay, so we will be seeing different population. We were not counting with the quasar.
Okay, thank you.
Hello, Pablo. Thank you for your presentation. There are many surprising features in these galaxies, I think, but you have not told many things about the compactness of this galaxy. There are a few tens of parsecs or 100 parsecs, and we have such an amount of star formation ratio, black holes, all in this small size, which is almost like a globular cluster. I cannot imagine how can this form it, but maybe you have some idea of why they are so compact.
your email in my box. So there is a variety in the little results. Okay, if you go to the COVID one, there's a paper where they claim 60 parsecs effective value. Okay, it was a long source. But also the vision was very dry and very broad. I don't think that's that's very much. Very good for you to have there. But I would say that there are results. Some of the little results will go to the blue, okay, and will go to the heated data to James, for example. You see things around. They are not as compact. In the UV, they are not as compact as in the red. Okay, you see the red blue, right? That's very difficult. There are many cases about this because data by shower and here or in uncovered, you don't really have a signal to understand what all this is. But there are more papers trying to understand morphology, and many of the results are extended. So now, I think, confirm that the UV part is already on the star, and that is more extended. And we are talking about several hundred parsecs. Okay, so similar to the model, quite small because 300 parsecs is not a large number for the sizes of these regions where you know to do 100. When you go to infrared, they are forming, so not much can be said. When that particular source, which is less, they put up with a size, but I need to be sure that I think we are talking about 100 to 100 parsecs. I'll say that that's too long, too large for a lower. So I think there is some structure there. But certainly, if you believe that only the UV is dominated by stars, or if you believe that there are stars more dominated than infrared, the stellar magnetism that you calculate is similar to the structure, but in a outbreak in another area. I think there is a lot more than you can terms of morphology.
Last short question.
Any evidence for variability? Okay, thanks.
Super short. So one thing I forgot about. So one of the, when you say how is it, the bad, the ugly, and the good, the bad, and the ugly, no? So the good was that there is an agreement that the universe at redshift beyond 10 was very efficient. But on how, sorry? Because you see bright emission that in principle should be. Okay, but even that, no, isn't there a bias also in that? Because how many sources are we talking about? Maybe we are just detecting like the 5 that are brighter, and then we are claiming that the universe was very efficient.
Studying very high sources, like meaning about 9 or 10. You compare the UV intensity with the very high values. Okay, so there I would say that we could only affirm that that the universe was repetitive from thinking before, because either to have an here and there, or many stars, different elements, or then to this. When you go to the fossil record, the galaxies are recorded worldwide that we are doing another work. You can do the astronomy, you are not affected by 80 men there. You are calculating the astronomy, that is stars. And you get that you have to form a lot of mass calculational masses. You can do more or less the same number instead of the masses that we're calculating for bring it started all the way to the uncertain. We get that many of those galaxies are already 3, 4, 5 to have calculational masses already 10, 15, even 20. So we think that there could be a lot of information that is going to 30. And that's the interpretation of that is only stars. So there, I would say that we could affirm that the universe was very effective, forming stars in the first 2 well, this is the start of the job of the number of things for the and I think the idea that is going to be as a truly possibility that the JWST opens for me is something that you can do much better than we have to do for we should do much better with the
Okay, so let's thank again Pablo for this nice presentation. Thank you all for coming, and please all the students come here to check if you are on the list. Thank you.